In the second part of section 6.6, we will study least squares fitting of other curves. Consider a regression model of the form, which is a quadratic function. We'll try to find the best fitting quadratic regression model for a given data set, xi, yi, I is 1 to m. As for the regression line, we'll get a linear system and try to find the least squares solutions of the system. For linear system, consider data points. From the first data point, we have predicted y value, that is the observed y value from the data. It's not the same in general, but we try to get a linear system. From second point, we have that one, and now from the last point, we have this equation. And these equations can be written as in this metric equation. Here, x is has 30 columns, and first column is all 1. The coefficients of beta 0 is all 1 here. Now, the coefficients of beta 1 are this, so the collection of the x coordinates, and from here we have a collection of x squared. Okay, for y, that is collection of the observed y values. Once we have a linear system, then we can find the least square solution by the method of normal equations. So we multiply x transpose in front of here and here. Then we reach at this formula. And you can see a pattern. And the summation will be the summation of 1, so that must be m. Right? This must be m, the same as m. And summation of xi squared. And now power of xi is increased by 1 here, and again one more time. And right side, this is summation of yi, power of xi, one more power of xi. So you can see the pattern. Okay. Find on least square curve of the form that best fits the given points. Let's try to make a table for the data. Okay, let's try to make a vertical table xy. Now x values are 0, 1, 1, 2. 0, 1, 1, 2. Y values are 1, 1, 2, 3. 1, 1, 2, 3. Okay. Now we have to make these normal equations. The metric, 3 by 3 metric. Summation of 1 must be 4. There are 4 points. Now summation of xi, which is 4. Now summation of xi squared. That is squared, squared, squared. 4, 1, 1. So that is a 6. And symmetric, we can put here. Oops, that must be 6. Okay. Let's, okay. Now that must be 6. And also, that one is square sum, which must be 6. And that one, and third power, 118, must be 10. Now, so that it must be 10. And now summation of fourth power, 16, that makes 18. Okay, that's the normal metric, and beta equals right side. Summation of yi, that is 7. Summation of xi, yi, multiplication is 1, 2, 6. So that must be 9. 1, 2, 6. Okay. Now summation of xi squared yi. So again, 1, 2. That must be 4 and 12. 1, 2, 12. That must be 15. Right? 1, 2, 12. Okay. So we can solve this problem by using elementary row operations start from augmented matrix. Okay, we write here the first row for 4, 6, and 7. Now second row, we directly apply row operations, replacement, subtraction. That will be 0 and 2, 4, 2. Okay. Now we multiply. Okay, 2 eliminated that one. We multiply here 3 over 2 and subtract. Okay. 3 over 2. Then there will be 6, so there is 0. Again 6, subtracted, and then makes 4. And that one makes 9. 3 over 2 is multiplied, and 9. 9 is subtracted to get here 9. And this one will make 21. Okay, 21 over 2, multiply that one, and subtract from 15. That's 30 over 2, so that the remainder part is 9 over 2. Right? Okay. Here for the, okay. Now, from here, okay, first we write down for 6, 7, the same for the first row, and that one is 1, okay, 0, okay, this 0, 1, 2, 1, right? And then twice subtracted, which makes 0, twice subtracted, that is 1, and twice subtracted, 4 is subtracted, remainder part is now 1/2. Okay, now from this one here, okay, we'll try to eliminate these two by using that. That is 4 for 6 times subtraction, that will be 0, and 6 times subtraction, that is so that 6 times 3 is subtracted, we have 4 here. Now that is 0, 1, and twice subtracted, that will be 0, twice subtracted, okay, this is 0, and 0, 0, 1, okay, half. Now, it's not affecting here 4 times subtraction, so that we can change this one 0 and divide by 4, which means that here we have, for the first row, that will become here now 1, 0, 0, 1. That means from here, that means beta must be 1, 0, and half. Okay, from this one, the least square curve must be y equal beta 0 is 1, and beta 1 is 0, so we have no linear term, and beta 2 is half, so that's half x squared. That is the final answer. Right? Oh yeah, we made the correct answer. Okay. Now, for these data points, you can do the exactly same to get the answer here. So try to do it yourself. Now, we can apply the technique for other curves. Assume that once you try to see the data points and you made a plot, scatter plot, and it looks like a combination of cosine x and sine x, then your curve, least square curve must be, can be formulated in this way, and then you have to find A and B so that the curve is best fitting the given data points. So always the idea is you have to make a linear system, and you should try to find the least scarce solution of the linear system. Okay, again, we'll try to make a table for the data points. Okay, that is 0 and pi over 4. That is second x point, and final one is pi. And y values are 0, 2. No. That is 1, 2. The first one is 1 and 2 and 0. 1, 2, 0. Okay. Now, for that one, once we are choosing the first one, then x is 0, so that a, okay, times 1, x is 0, cosine 0 is 1, plus b times 0 must be 1, right side 1. And from pi over 4, we have a times cosine pi over 4 is 1 over square root of 2, plus b times sine pi over 4 is same, 1 over square root of 2, which must be now right side 2 y value. Now x is pi, then there is a times cosine pi is minus 1, and plus b times that's pi, then it'll be 0, and right side must be 0. The y value is 0. From this one, the linear system can be obtained in this way. The coefficients, here there's first column must be 1, 1 over square root 2, and minus 1, 1, 1 over square root 2, and minus 1. Second column, 0, 1 over square root 2, and 0. Right? Okay, there is 0, 1 over square root 2, and 0. And here we have the parameters a and b, and right side that is 1, 2, 0. Right? Okay, again, we can use the method of normal equations. So from this one, the normal metric must be 2 by 2 metric. Dot product of this column must be 1 plus half plus 1, so that 2 plus half, so that 5 over 2. And now this two dot product must be half, right? And we know that it's symmetric. Okay, and then the dot product itself will make here half. And now that the parameter AB, and then right side, okay, we make this dot product, and 1 and 2, which means that there's 1 plus square root of 2. And now for that one, this dot product makes here square root of 2. Okay. Okay, we have to solve that one. Looks like these are linearly independent, so that we have unique solution. And we multiply 2. Then that is, okay, for simplicity, multiply 2 every then 5, 1, 1, 1. Now that is the parameters AB, and then this one is the same as now 2 plus 2 square root of 2 and 2 of square root of 2. Okay. Okay. Now augmented method, can we apply the elementary row operations. Then from here that is 1, 1, 2 square root of 2, and then 5 times subtracted is a 0, and minus 4, okay, subtracted, and minus 4, 5 times subtracted, so that is 2 minus, okay, the 10 square root of 2, so that minus 8 square root of 2. Right. Now we scale by minus 4, so that the bottom row will become 0 and 1, and minus half plus 2 square root of 2. And now we try to subtract, then there's 1, 0. That one will be subtracted, so that, okay, then it will make here half, and this will disappear. Okay, so we reach at this one. That means A is half and B is minus half plus 2 square root of 2. Okay, we got the right answer. Okay, so we found here A and B, and if you plug here A and B, then that will be the best fitting curve for the data points. Okay. And sometimes you will make nonlinear model. Then if you try to solve nonlinear model, then it's very hard. So that we may try to get linear model by using change of variables. For example, the model you are thinking is here y equal a plus b over x. Then we try to get new variable x tilde is 1 over x, and we don't change y, but anyway we try to use y tilde equals y. Then that one will be y tilde plus x tilde times b. So this one is now linear model. By introducing change of variable, we can get linear model. Of course here, now, and along with that, in the data set, there's no zero value. Of course, if there is some zero, then you may have some problem, because in new data, you have to make 1 over x. So it change of variable means the transform data also. We'll see in this example. Now for this one, in this case, once we consider reciprocal of that part, then it is some linear, so that rather than y, we are trying to use y tilde, which is 1 over y, then, and x is not changed. Then here y tilde is the same as a plus b x tilde. Again, this is a linear model. And for this one, this is exponential model. And if we take and logarithm, okay, let's try to apply natural logarithm. Then the same as, okay, natural logarithm of c. By using logarithm formula, we can get that one, logarithm e to the dx. Logarithm e, they are inverse each other, so we can reach the logarithm c plus dx. Right? Okay. Now we introduce y tilde here to be logarithm y, and for x we don't need change, but here we are using x tilde. Then this equation becomes y tilde equals d x tilde plus logarithm c. So this is a linear model. Here the idea is we try to transform the nonlinear model to produce a linear system. Once the model is linear or polynomial, then we can get easily a linear system. And once we get a linear system, then we can use the normal regression technique to get least squares solutions. Okay, let's try to solve this problem. Find an least square curve of the form y equal c times e to the dx that best fits the given points. Okay, here now, once we see the table of the data points, then x is 0, 1, 2, and y values are e to the 3, e to the 5. Now, when we try to get linear model and linear system, then change of variable is this one, y tilde is logarithm y. Change of variable means transform the data. So this data must be transformed. And here y tilde is logarithm y. So from this y value, we apply logarithm, natural logarithm. That must be 1, that must be 3, that must be 5. Now, for this one, here we may consider this as x value, there's y value. Then for linear, the regression model is first in the matrix system, first column must be all ones. This is collection of x value. This is collection of y values. Right? So exactly from here we get that one. Now we have to solve this one. Then the solution will be here, that is logarithm c. Once we solve this problem, then solution must be that is logarithm c and d. Okay, let's try to solve this one. And x transpose x must be here 3, and now dot product is now again 3. So here we have 3, and that is now 5. Okay. Dot product itself is 1. Dot product will be 1 plus 2, so there are 3. Okay, that must be 3 again. Dot product itself will be 1 plus 4, must be 5. Okay. Now, x transpose y, that must be the dot product along with this one, that one. That is same as 9. And this 2 makes 3 plus 10, 13. Right? Okay. So from here, the augmented matrix, the first row will be 3, 3, 9. After scaling, it becomes 1, 1, 3. And that is now subtraction. Okay, we'll try to subtract. That is 0. That is 2. Okay. And then that's 4. So here we have, that is 0, 1, 2. And we subtract then 0, 1. 2 we subtract, that is 1. So that means here, now the output, that one, oops, okay, that is now 1 and 0. This is the reduced echelon form, 1 and 0. So that means this last column is exactly here logarithm c and d. What is c? C is exponential of 1, which is E. Okay, so we have the final model, best fitting model, that is Y equals C is E times. Now D is 2, so that E to the 2x. So we may write this one E to the 2x plus 1, right? So that's the final answer. So by transform the nonlinear model, you can get linear model, and finally you can get a linear system. Once you get linear system, then always you can get the solution. Sometimes you cannot get, once the normal metric is not invertible, then occasionally you cannot get yet. However, and the way of solving the problem is now try to get normal equation and then solve it. Then that is the least scarce solutions. Here we follow exactly the idea and solve one nonlinear model. Okay. Okay, that's the end of the section. Thank you.